Hello again and welcome back. We're going live with another stream today, so welcome to Freaky Physics. And again, today we have Geeta. We'll just finish what we were doing yesterday, and we do have a few new problems. Yesterday we did have some glitches with what we were doing, so hopefully today there are none. So okay, let's go in and let's enter the classroom. Hi Geeta.
Hello.
Hi. Sorry about that. Yeah, the traffic was really bad today. I don't know. Holiday rush, I guess.
Perhaps
Yeah.
it's no problem.
All right. Anyway, so you sent me over a few new problems, and then we still have a couple of problems from yesterday, right? So
Yes, if
let's.
it's too much, then we'll just do them next time.
Yep. I guess we can do those problems from yesterday first, then, and then let's see. 2, 3, 4, 5, 6. Yeah, I think we can go through all of them today. All right.
Great.
To make it a bit easier as well to see, I'll just share the board as well on the screen. Okay, like that.
Okay.
All right. So let's get on with it. Let's see what we have next. Okay. So our next problem here involves equipotential lines. I'll just copy that here. Let me get on the stream as well and put that up.
Okay.
Okay. All right. All right, so first of all, we have the surface of P is an equipotential. P is the planet in question here. Dotted circle E1 has equipotential line given, 3r/2 from the center of P. The potential difference between those two is 2.2 times 10 to the 6 joules per kilogram. The radius is given below as 8.5 times 10 to the 6 meters, and we'll estimate the magnitude of the gravitational field strength. Okay. Easiest way to go through this problem is to go and compare the equipotential, or rather the gravitational potential equation and the gravitational acceleration equation. Okay. Data booklet. Let's open up the data booklet for now so we can get the formulas. Okay, hold on. The data booklet's still opening up. All right, here we go. So the idea here, I'll just write the equations first to make it easier for us to see. The the equation for gravitational acceleration is this: G equals big G, big M over R squared. Okay, and then the gravitational potential Vg, we'll label it like that. It's going to be big G, big M over R. There's there should be a negative in here, and so should also should be have a negative sign there, but we can ignore those for our purposes, right? So if you look at this carefully, you can easily see what the relationship between these two are. It's just that Vg is equal to G times R. Okay, and this is gonna be the equation we will use to find the gravitational fields the field strength difference between the two equipotential lines. Okay, so so all we have to do now is let's just rewrite this. We are looking for G, so in this case we'll just rewrite this as G equals V G over R. Okay, so all we have to do now is find the two values of G. So in this case, G1, G0 rather, would be equal to V0 times, sorry, not V0, but E0, equipotential, right? E0 and R. in this case, over R. Okay, our R here is this value here. So let's just keep it as R first. And then G1 will be equal to E1 over our the new distance here is 3R over 2. Over 3R over 2. Okay, so since we're now looking for the difference, this is now going to be equal to, so the difference in the G, okay, sorry, estimate the magnitude of the gravitational field strength between E1 and E0. Hold on. Estimate the magnitude of the gravitational field strength. Okay, all we're gonna do now is just put our values in here for both, find G for both, okay? So we just put our value in. Okay. So the potential, it's already given here that the potential difference between that, okay? So it's given that delta V, so delta E would be equal to E1 minus E0, and it's already given as 2.2 times 10 to the 6. 2.2 times 10 to the 6. All we have to do now is to find this G. We can just do that. G will be equal to this delta E over, because it's just an estimate, we'll just use either R or 3R over 2. I'm just going to use R in this case. Okay. And then all we have to do now is put this in. Put this in for delta E. And then use, okay, so 2.2 times 10 to the 6. Divide that by 8.5 times 10 to the 6 as well. So the 10 to the 6 cancels out. That is going to be a tiny value for G. Okay. Okay. Now, why is that okay? Even though we didn't really calculate it properly, why is this okay? Because of the word estimate. Okay.
So the G is usually small also.
Yeah. Yeah. Okay, so once we calculate that, what value would that be? So that's going to be, that should be approximately 0.25. Okay. Okay. I'm actually curious what the actual answer is. I'll just look at the mark scheme later, see if we see if this is more or less correct. But it should be. Okay.
Okay.
All right. Oh, sorry. Okay, sorry, I forgot. There should be a delta R there. So that's the formula. Okay, found the formula now. So this I forgot this. This should be a delta R here. So that's not gonna be 8.5. It's gonna be the difference between the radii. So it's gonna be 1/2 R. 0.5 R. Okay. So that's gonna be we'll still put the 8.5 times 10 to the 6. So it's still gonna be here times 10 to the 6. So it's still gonna be the same. That 10 to the 6 cancels out, but we have an extra term of 0.5. Okay.
Wait, sorry, I don't understand why. Why do we have 0.5?
Okay. The formula for the gravitational field strength. Let me just get that here. It's actually in the data booklet. This was not in the old data booklet, so this is now in the new one. Okay. The new data booklet actually indicates this formula here, that the gravitational field strength is equal to the difference in potential divided by the difference in the radius. So there should be a negative here, by the way. Okay.
So the 0.5 is the 3 over 2R minus the R.
R. Yes, that's correct.
Okay.
So 0. I'll just put this in a different color. This comes from 3 over 2R minus R is that. Okay.
Yeah.
All right. Anything else you'd like to ask here? If not, let's
Um.
move on to the next bit.
Yeah, we can move on.
All right. Um, okay. Then we have a second problem still related to that. To this problem here. Now you have another E2, another equipotential line, so that the potential difference between those E2 and E1 is also 2.2 times 10 to the 6 joules per kilogram. So draw the equipotential line E2 on the diagram. Okay, so remember that let's put it here, delta E. Yeah, we'll use E in this case because that's the letter used. This should be equal to E2 minus E1, and this should also be equal to, let's use the formula, G big M over R. Let's put nu here, right? And then minus G big M over 3R over 2, right? And we know that this is going to be 2.2 times 10 to the 5. Okay, so all we have to do now is find the value of this new R, right? We also know this already. We know the value. Actually, we don't, right? Okay, now, how do you find this? Let me,
We can find R.
yeah, we find this new R here, right? Okay, now, it seems to be a long calculation though if we do it like that, so there has to be a shortcut, right? But let's, especially with the space you're given, you're only given this much space. Okay, so what we can do is think about it this way. Okay, let's take a look at the pattern instead of trying to look at the formula. What's the pattern here? If R doubles, delta E, delta E decreases by half, right?
Mm,
Okay,
yeah.
so that's the idea. So what we do is, instead of doing it like this, we know that at R, it's got some value, E0, right?
Yeah.
And then from,
Wait, sorry.
go ahead.
Sorry. But wasn't it E proportional to GR?
It is G over R. It's not over R. It's not R, yeah. It's over R. So in other words, yeah, when you double the radius, you decrease it by 1/2. Yeah. Okay.
Okay.
All right. So going back here, so that, so okay, so when this happens, okay, let's reason it out now. When R increases, I'll use it like this. When R increases by 1.5, E decreases by what was that? 2.2 times 10 to the 6, right?
Yeah.
Okay, so this is what we're gonna use instead of just looking at the formula. So now if we're gonna look at this now, so if we're gonna start with 3R over 2, it should increase by, I'm gonna use the 3 halves, so times 3 halves. So that's gonna give us 9/4 R. Okay, then this means uh it, okay, so this should mean it should increase by this much as well. Decrease by okay, so by, this is a plus though, this is a plus, so how do we make that? Okay, so when increased by 3, Okay, there we go. When it increases by 3, it increases by 4.4. I think that's the easiest way to do it here. Okay, so that's the idea. So basically your R2 will now be equal to 3R, and that is what you will draw in here. So 1, 2, 3, 1, 2, so 1, 2, 3, 1, 2, oh sorry, it's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So you're just gonna draw the circle that's a radius 3R around the planet, something like this. This should be accurate enough since this is gonna be hand drawn.
So the relationship is. I didn't understand what were the variables of
Okay,
3 and 4.
so let's do it again there. Okay, so I think I will erase what I wrote. Let's redo that quick. Okay, so okay, so where was it? Okay, so the idea here again is, let's use blue. If R increases by a factor, I'll just do it like this, by a factor of A or X, I'll use X here. E decreases by a factor of X. In other words, so this is gonna be multiplied by X, right? This is gonna be so times X. Okay, hold on, I'll change the letter so it's not too confusing. Not X, let's say by a factor of N. Okay, so this is multiplied by N, right? This is also decreased by a factor of N, so this is going to be divided by N. Okay, so what does it mean? So let's, if we go back here, okay, so if we go back to the original one, that at R0 we have some potential V0, right?
Yep.
Okay, and then at 3 halves R, in fact, let's not use R0, just R. At R, V0, and at 3 halves R, we have some potential V2, V1, right?
Yeah.
So, okay, so what happened here? This got multiplied by 3.5, right? Sorry, 3.5, 3 over 2, right? So this means going here to here, this is going to be divided by 3.2. Okay.
Oh, okay.
Okay, so what's gonna happen here now? So what if we do the subtraction, v0 minus v1? If we do the math first, this is gonna become v0 minus 3v0 over 2, and as we mentioned earlier, this is gonna give us negative 1/2 v0. We can ignore the negative for now though, right? Okay, now however, we also know that this is gonna be 2.2 times 10 to the minus 6, right? Okay, all right, so we'll keep this in mind, but we will not solve it just yet. Now the next thing we're gonna look at is from v1 to v2. This is also gonna be divided by some number n. We'll call it n for now, right? And at the same time, this means we're gonna multiply this by some number 3n over 2 r now, like that, right?
Yeah. And sorry,
Go ahead.
V is constant the whole time. It's the 2.2.
Yes, this is gonna be v2 v1 minus v2 will now be equal to 2.2 times 10 to the 6. Okay, so this is the long way of solving it and the proper way of solving it. Okay, so if we do this though, What you notice some okay. If you do this, remember that this is also actually we don't have to do that. If that's 2.2, what was my train of thought again earlier? Okay, if the difference is the same, and this is also equal to v0 minus v1, right?
Yeah.
Okay, if they're equal to v0 over v1, then that tells us one thing, that v1, okay, let's just do the math real quick. Let's just compare that. So v1 minus v2 equals v0 minus v1, or 2v1 mathematically will be equal to v0 minus v2, right?
Yeah.
So in other words, this you can already tell us that okay,
So I
so
think it would be
basically
plus.
this is also gonna be equal to, you're gonna divide this also by 3 halves. That's what it means.
Yeah.
Okay, and because of that, then that means our n is actually also 3 halves here. So we're gonna have to do 3 halves squared, and that's gonna give us 9/4 r. Okay.
Yeah.
Okay, so our new r 9/4 r would is approximately what, 2.2 and 1/4, 2.26. So it shouldn't be 3 here. Okay, it should let me just lock this real quick. Okay, lock. This should be around 2.5, the 2 and 1/4 radii away. So 1, 2 and 1/4 should be here. 1, 2 and 1/4, 1, 2 and 1/4, 1, 2 and 1/4. So there. That's the answer. Right?
Okay.
Okay, I think
Yeah.
that's a better one. All right. Any questions here?
No, it's clear.
All right. Okay, let me look at the rest of the other problems first. Let's see one that's related to gravity. Gravity, that's electricity. This one's different. Okay, let's do this gravity equation here. All right, for gravity, okay, this next problem about gravity is about the escape velocity. Okay, so while the, okay, here we go. The question is loaded. So you're given the escape velocity for for the Earth, on the surface of the Earth. Also, is there, yeah, there is an equation in the data booklet that states what the escape velocity is. I'll just place it here right away. The equation is a square root of 2gm over r, like this. Okay.
Yeah.
Okay. All we have to do now is we are going to, because again, we're comparing, the fastest way to do this is to do a ratio, right? So all we have to do now is I'll just do moon like this, okay? Over V, the escape velocity on Earth is V escape. So I'll just put it like that. It's gonna be, well, shortcut, I'll just do a big square root, right? 2g, the mass of the moon, over the radius of the moon, right? Over 2g, mass of the Earth, over radius of the Earth. Okay. What cancels out immediately? The 2g. So we rewrite that v moon equals v escape times the square root of v the mass of the moon times the radius of the Earth over the mass of the Earth over the radius of the moon. Right? And the
Yeah.
beauty here now is we don't need to know what these masses are because we are given the values. So the diameter is 4 times smaller. That also means the radius is 4 times smaller, right?
Yeah.
So what we're gonna do here, this is gonna be V escape square root of it's gonna be 4 over 1, right? So this part's 4 over 1, and this part's gonna be 1 over 81. You notice the numbers are perfect squares.
Yeah.
4 over 81. We take the square root of that now, and that's gonna be 2 over 9. V escape. And our final answer?
Oh.
C.
See.
Okay. All right. I think that's the last problem you sent over for gravity. Let me double check. That's pressure. Bicycle. These two are together. This is resistance. This is part of this. Okay. Yeah. Let's go now to the last multiple choice problem here, the one about resistance.
Okay.
Okay. So, all right. For resistance, still loading. Okay, so the resistor has a resistance R connected to a cell of negligible internal resistance. The power is dissipated in the resistor and discharges the cell in time t. Okay, an identical cell is connected in series with two identical resistors of each resistance R. What's the power dissipated and time taken to discharge the cell? I think this means for second circuit, right?
Yeah.
Okay, now before we go there, now let's go back to power. Power is in electric circuits or in resistors would be equal to IV. Okay, that's in the data booklet. And then to find the time to discharge the cell, there has to be some time, right? And the time here, the best way to calculate the time would be the current, okay, would be the charge in the battery divided by the current. Okay, now we will not be actually be using these to calculate anything. We'll use the ideas either way though. Okay, now if we look at the two circuits, okay, so on the first circuit, let's just draw the circuit real quick to make it easier to see. Okay, you have that, and then you have two resistors in series, right?
Yeah.
Okay, so in this case, the total resistance is R. This has a potential difference. We'll call it V to make it easier. And this has a total resistance 2R, right?
Yeah.
Okay, this also has some value. This still has the same value V. Also, the battery is going to contain a certain amount of charge Q, which would be identical in both cases, right? Okay, so this already is going to be easy to solve because all we have to do now is look what I is. I in this case would be equal to V over R, right? And
Yeah.
I'll label this as I1. Okay, now in this case, our I2 here is going to be slightly different. It's still going to be V, but our R is 2R now, right?
Yeah.
Now, you can calculate this, but you can also easily deduce that since the current, in this case, I2 is equal to half of I1, right? You can deduce that easily from these two. This also means that the time for the second circuit should be equal to it discharges slower because there's less current, right? So it's gonna be hold on, is that right? Yeah, that's gonna be 2 times T1. Okay, so we can already see which ones we can consider. We can consider B or D to be correct. Okay,
Is that Because time is directly proportional to the charge.
Yes, correct. And the charge would be, because it's the same battery, then the charge in both circuits or both cells would be identical. So half the current, twice the charge, at twice the time. Okay, for the same amount of charge. Now, similarly, there's another equation we can use for power. There are three versions for the power equation. That's the first one we wrote is the main formula, but we do have another one. We have power equals I squared R, and we have power equals V squared over R. Okay. Now, from here, what's the easiest one to use? It's V squared over R because the V is constant, right? So all we have to do is just compare the resistances. Because the V's are constant, then that means the bigger the resistance, the less the power, right?
Yeah.
And our answer here is gonna be D. Okay, why? Because in this case, let's do the first one here. The power will be equal to V squared over R. Let's just write it like that, right? But the power on our second circuit will be equal to V squared. It's still the same V, but our R is 2R now. 2R. So comparing these two, P1 and P2. Okay. Comparing P1 to P2, P1 is equal to twice P2. Is it? Yeah. Or rewriting that, P2 will be equal to P1 over 2. And that's our answer for D. So the final answer will be D.
Okay.
All right. Okay. Which one is shorter between these two? Okay, this one's still related to electricity, so we'll do this one. Copy this. Okay, so you have a girl riding a motorcycle powered by an electric motor. We're given the charge and the EMF of the battery, like that. Okay. Maximum speed is given for part A with energy from the battery alone. So 20 kilometers. Show that the time taken for the battery to... Oh, this one's pretty easy. A is pretty easy. You don't even need any of the given information from here. Okay. This is easy because all you have to do is you're given the speed, you're given the distance.
Sorry, but what do they mean by battery to discharge?
Where does it say that?
And the question.
Yeah. This part, right? Okay. So whenever you have a battery, it has a certain charge to it. Okay. Now, ideally, batteries, when you use them, they keep the same voltage, and all you have to do now is, for the same voltage, they will always provide a certain amount of current. Okay. And because the current involves charge moving around, that means the charge, when it discharges, it cannot move any of the charges anymore, and the current runs out. Okay.
So to use all of its power?
Yeah. So it uses all of its power, in other words, correct. Okay. However, in this case, because you are given the charge, this is Q, right? That's another way of thinking about it. So when you discharge a battery, you either use up all the charge inside of it, or you use up all the power.
But in our formulas, we have nothing that tells us how much is left.
That it doesn't matter, because think about it this way. If there's let's think about it this way before we solve this. Okay, so let's say that I'm just gonna visualize this. What if this is initial? Let's say that the power, the battery's power is this, right? Okay, then at the end, okay, you can imagine that the battery's power is somewhere just here. It still has a little bit, right? But in this case, how much did you actually use up It's only this much used up, right?
Yeah.
Okay, now, in other words, this part that you used up, this is the useful energy. And that means that from here on out, even though there's still energy left over here, right? It's not useful. So, because you cannot take it out of the battery anymore. So this is where it's already discharged. Fully discharged. Okay. Now,
Why can't we use? Sorry.
go ahead.
Why can't we use the remaining energy?
That goes into chemistry now, not into physics. But suffice to say for now that there's no such thing as whenever we try to charge any sort of battery, there's always that leftover voltage that if you try to go below it, either you cannot go below it because it's going to be very inefficient, or it's going to damage the battery otherwise.
Huh.
Okay, now a very good example for that would be your phone batteries. At 0%, your phone battery still actually has around 3 volts of power left in it. Okay,
Huh.
but when you go below 3 volts, actually if you go below 2.5 volts for your phone batteries, the structure starts to change, so that when you try to charge it up, there's a risk of it exploding.
Oh,
So that's why.
that's
Okay,
really interesting.
yeah. And then you can also you can actually charge it to a really high voltage, like maybe 5 or 6 volts, but that wouldn't be safe as well. So your phone batteries are charged 100% charged at 4.2 volts instead of 5. At 5, there's a risk of it exploding again.
Oh.
Okay.
Okay.
All right. So anyway, so that's a little bit of the chemistry and an application. So, but that doesn't really matter for our problem, right? Okay. So if you look here, part 1 is quite easy because you're already given the speed and the distance. All you have to do now is find the time. How do you do that? Time is equal to distance divided by speed, or we'll use v for speed. Yeah, so that's gonna be 20,000 meters divided by 7.0 meters per second. So that's approximately 3. Well, if it's show, remember you need to give it to a certain number of decimal places. So 20,000 divided by 7 would be how much? 6. No. Oh, that's gonna be hard. Let's just put that in a calculator. It's 20.
Yeah.
Okay. 20 divided by 7 is 2.86 times 10 to the 3 seconds. Okay. All right.
Yeah.
Deduce the average power. It's 240 watts. So you need to find the energy or the power, right? Okay, here's the shortcut. Remember that power equals IV, right?
Yeah.
Okay. What I don't normally teach the energy form of this. I just usually ask students to kind of see why we get it. Now, if you think about it, power is energy over time, right?
Yeah.
Right? V is still V, but I, current, is charge over time, right? So the time cancels out here. So we get another formula here that basically says energy equals QV. The Q is given 43 kilocoulombs and the voltage is 16 volts. So just put that in here. That's going to be, where was that again? Q is 43 kilos, so 1,000 coulombs, and then V is 16 volts. Multiply that, we get our answer. So 16 times 43,000 is gonna be Okay.
688.
Okay, 688 thousand, right? And this is going to be in joules. Now, all you have to do now to get power is divide this by, we'll use 3 because it's the one given. We can use 3. Okay, so power will be 688,000 divided by 3 times 10 to the 3 seconds joules. This is going to give us the final answer. Divided by 3,000. Okay, let's do that here. Divided by 3,000. That's going to be, and I think I missed something. Oh, what if we use a 2.86? 688 divided by 2.86. There we go. So that's going to give us, so 2.86. That's going to give us 240.6 watts. Okay. Which is, again, close to what we have. All right.
Yeah.
All right. This next problem, it's related to this, but let's take a look at this now. This involves now friction and air resistance acting on the bicycle when they move and the girl. So assume that all the energy is transferred from the battery to the motor. I think we're no, we're not. Okay. Determine the total resistive force that acts on the bicycle and the girl. Now, okay, the idea here now is the girl, is it given that she's moving at a constant speed? No, it's not. Okay, we are given a distance though, right?
Yeah.
Okay. Okay. Now here's the thing about it. You can think about it this way. The work done by the frictional force should be equal to the frictional force itself, right? Times the distance traveled. Okay. Hold on. Is this gonna work? Determine the average resistive force. Actually, yeah, we can deduce this because so if we assume, so assume constant or uniform speed, right? Now, this will work because this means that whatever the force that the motor is doing, so the work done by the motor should be equal to the work done by friction. Okay, and therefore all we have to do now is this is going to be 240 watts. 200, no, let's not use the watts. Let's use the 688. So that's going to be 688,000 joules here should be equal to the frictional force times 20,000 meters. Then from here, we just get the final answer. The frictional force will be 688 divided by 20. Divided by 20, that's going to give us 34.4 newtons. Now, this is usually, just so you know, this is one of the more challenging questions because normally when you think force, you're looking for an acceleration, right? So if you're not given an acceleration, you assume that this is the case. Work done is equal to force times distance. Okay, so works if acceleration not given. Okay. All right.
Okay.
Okay. All right. We have 6 minutes. I think we can do the last problem. Okay. The last problem here is about pressure. Okay. Copy this first. Okay, so you said you already know how to do A, so we'll skip that. Let's go straight to B. So you have a tube. So we'll ignore the first part of the problem. Okay. Okay. So B, you have that tube of a circular cross section sealed at one end, contains an ideal gas. Oh, this one's a bit tricky. So show that P0 plus PM times 0.190 is equal to nRT over A, where all of these values are given here. Okay. The one thing that, okay, I want you to notice one thing here. Okay. If you notice, it says here that the mercury column, okay, you seal the one and okay, we're gonna assume that this mercury column is stationary.
Okay.
Okay. Now, we have to assume this because that's the easiest way to solve it. Okay. Now, think about it this way. This mercury column, there are three forces acting on the mercury column. Let's identify the three forces first. Yeah. Why do we need forces? Because pressure in the most basic treatment is still about forces, right?
Yeah.
Okay. So if we look at it this way, this is gonna be the weight of the mercury column, right? Then what are the other? What's another force here? There's the atmospheric pressure here. Pressure from the atmosphere, right? And then the third force is going to be the pressure coming up here from the gas, P gas. Okay. Now, the reason why we have to do this is this mercury. I'll just call it pressure from the mercury as well. Now, this will work because the pressures are all equal. No, not the pressures, but the areas are all equal. Okay, since areas are equal, the force ratios are equal to pressure ratios. So that's gonna make it easy to solve. Okay. Now that we know that the pressure ratios are the same, now what can we do here? Now what we can do here simply is I'll just set the equation up here. The pressure from the mercury plus the pressure from the atmosphere should be equal to the pressure from the gas. Okay, so this is the most important thing we can get from this diagram. Now let's proceed to solve it. Since the mercury it's already given. It's already given that this is PM. Okay, so let's change the label. PM here, PM here. Yeah. P0 is also labeled as P0 here. And okay, now that's gonna be easy now. We don't need to know those values, so we now have that. Okay, so all we have to do is derive the formula. So P0 plus PM should be equal to the P of the gas. We're almost there, right? Now, the pressure of the gas, remember the pressure of any gas using the ideal gas law. So PV, let's just use it like this. PV equals nRT, right?
Yeah.
Okay. Okay, here's the thing. What is A here, the cross-sectional area of the tube? I'm going to say that the volume will be equal to the height times the A, right? So, okay, so that's gonna be where it is. So this is gonna be the height, and this is gonna be the cross-sectional area here, A over there. Okay, so from here we can see where the over A comes from already, and we know that the height is 0.190. So all we have to do now is put everything in. So when we put everything in, this is gonna be P times 0.190 times A equals N R T. Okay, so all we have to do now is substitute this into here, and move this, sorry, not that, move this A to the other side. And that's, when we do that, we get that. Okay, so P0 plus PM times 0.190 is equal to nRT over A, shown. Okay.
Yeah.
All right. Last question. So it's rotated. Copy image. Okay. So we still have the same tube, but now it's rotated, flipped upside down, right?
Why would that matter?
Because now the diagram is gonna be slightly different. Okay. Earlier, when it was right side up, it was the atmospheric pressure pressing down, and the gas pressure pushing up. Now it's the other way around. The mercury pressure is still gonna be PM, still gonna be downwards, but this time it's gonna be P, the pressure of the gas going down, and the pressure of the atmosphere, P0, pointing up. Okay. Now, because of that, this mercury column changes. The length of the column changes. But since the temperature doesn't change, then that means what? This part, we can use one of the gas laws. Which one is it? Since it's a temperature that doesn't change, we can use Boyle's law. P1 V1 equals P2 V2, right?
Yeah.
Okay. So all we're gonna do now, we know what was the initial pressure. We don't know the P of the gas just yet. Yeah. So in this case, P1 times 0.190A should be equal to P2 times 0.208A. So the A cancels out. So we're going to get that P2. So from here, P2 will be equal to 0.190 over 0.208 P1. So that's the first part we need. Yeah.
Yeah.
Okay. However, what can we get here again from the diagram? That let's label this P2, right? That P2 plus PM should be equal to P0, atmospheric pressure. Yeah.
Right.
Okay. But also, let's just write the formula from above, from the previous problem, relating to 3. It is PM plus P0 equals P1. Yeah. So PM plus P0 equals P1. Now we're going to put that in here and put these facts in and solve for P0. So basically, let's label it, solve for P0, right? Okay. So all we have, okay. Now what are we gonna do? P2 will be equal to P0 minus PM, right? So it's P0 minus PM in this case. It's gonna be 0.190 over 0.28. Our P1 is PM plus P0. Okay, and then from here we can do the math pretty easily from now on. We just put this in and solve for P0. Yeah.
Okay.
Okay. So what are we gonna get? P0 times 1 minus 0.190 over 0.208 will be equal to PM times plus 1. So 1 plus 0.190 over 0.208. Okay. Now the problem now is, the last thing we need to know is what PM actually is. Right? But how do we do that? We can get PM from part A. This value here, if you think about this mercury column here is a cylinder, right? So all we have to do is do this. Density of mercury times G times the height of the mercury column of 0.035. So this is the last portion, and then from there we can solve what P0 is. So Pm will be equal to density times G times 0.035. Okay. Okay. So from here, substitute in here, solve for P0. Okay. I think the only problem here from now on is actually knowing what the density of mercury is. Is it given? Yes, it's given. Since the density of mercury is given, we can solve for it. Okay. At this point, I will not finish it because I'll just finish the last bit. Here, outline what the gas particles in the tube hit the mercury's surface less often after the tube has been rotated. This is very easy. Pressure decreased, right?
Yeah.
After rotation. And because of this, as the pressure decreased after rotation, hence, not yet. While temperature, I'll add that. While the temperature is constant, right? So this
Yeah.
means collision speed is still the same. But less frequent collisions. Okay, that's it. Okay, all right. Okay, I hope everything here is clear. Anything else you'd like to ask before we end? We did
No,
go a bit
that's
over
it.
time.
I'll go over it now again, and then if
All
I have
right.
any questions.
Here's the thing, since I'm streaming this, right? That means you can actually access the video again later if you want to. I'll send you
Okay.
the link to the channel. Okay.
Okay, thank you.
So if you want to watch it again. All right. So with that, I'll just end it here. We'll see each other again next time. So you have a good day and bye bye.
Yes, thank you. Bye bye. Have a nice day.
You too. Okay, so that's the end of the lesson. Back to the stream. Okay, that's a lot of problems. Now, what I'll try to do here today is, well, not today, but maybe in the near future, is we'll break these into smaller problems, just like we did before, and turn them into shorts. And here's the good news about shorts in YouTube. I think they've been extended to more than a minute, so that means we don't have to break it into parts anymore. Okay, so what we'll do, again, we'll break these into smaller bits and see what we get. So before we end for today, don't forget to like, share, and subscribe to the channel. We are again on YouTube, Facebook, TikTok, Instagram, and Twitch when we go live. So don't forget to subscribe. So that's it for today. So I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everyone. Bye bye now.